Volumes and surface area. In all the previous geometry lessons, we looked at shapes in 2 dimensions. Now we're going to step up to 3-dimensional figures. In 2D, we could talk about the area of shapes. In 3D, we will also talk about the volume of shapes. We'll start with the easiest of 3D shapes, the cube. Very special shape. And of course, a cube has 6 faces, 6 sides, and these are 6 congruent squares. It has 8 vertices and 12 edges. And it's true that at every edge, 2 faces meet in a perpendicular manner, and at every vertex, 3 edges meet mutually in a mutually perpendicular manner. So it's all right angles, all the meetings of edges and faces. A square has an edge length of s, then its volume is given by s cubed, s times s times s, or s cubed. And in fact, when we raise a number to the 3rd power, we call this cubing the number precisely because this is how we find the volume of a cube. So just the words squaring and cubing are actually geometrically grounded. They're actually connected to the shape of a square and the shape of a cube, even though we use these terms when we're in a non-geometric context. Each face on this cube is a square with side s, so each would have an area of s squared, and of course there are 6 sides, so the total surface area is 6s squared. Those are the 2 formulas for the cube, and those are both good ones to know. And again, don't just blindly memorize these. Actually think these through and understand why these are true, but these are good to know and good to be familiar with. The cube is the special case of a more general category known as rectangular solids. So the sides of a rectangular solid can be rectangles, but we still have the requirement that the faces meet at right angles at each edge, and 3 mutually perpendicular edges meet at each vertex. So there's still right angles everywhere, just now the lengths are different. So a rectangular solid, some people might just think of this as a box or something like that. The volume is the product of the 3 different edge lengths. So volume equals height times width times depth. The surface consists of 2 h times w faces, 2 h times d faces, and 2 w times d faces. So the total surface area is this. Again, these 2 formulas, the 2 formulas for a rectangular solid, it's very good to be familiar with these formulas, but again, do not blindly memorize them. Make sure you understand and can reproduce these on your own. In rectangular solids, we can consider 2 different kinds of diagonals. One kind, called a face diagonal, is the diagonal along only one face of the solid. So for example, on the front rectangle, we have this line AC, and of course we see legs of 3 and 4, so we know it's a 3, 4, 5 triangle. We could just use the Pythagorean theorem, so AC equals 5. And so that is just connecting across one face. It's still on the outside of the rectangular solid. The other kind, called a space diagonal, this actually goes to the inside of the solid. It actually goes through the absolute center of the figure. So it passes through the interior from one vertex to an opposite vertex. So here, from A to D. And so A and D are not along any face. There's no single face that contains both A as a vertex and D as a vertex. They are opposites. So for this, we can use a 3D version of the Pythagorean theorem, where we just square the 3 individual leg lengths, and then that will equal the square of the space diagonal. So here, we're going to add up 9 plus 16 plus 25, so that adds up to 50. So the space diagonal AD equals the square root of 50, and of course 50 is 2 times 25, so we can write square root of 50 as square root of 25 times 2, and the square root of 25 simplifies to 5, so this is just 5 root 2. That was a whirlwind tour of simplifying radicals. If simplifying radicals is something that's not familiar to you, please watch the video on simplifying radicals, where this is discussed in detail. What is the length of the space diagonal of a cube of edge length s? Well, again, the 3D Pythagorean theorem, ab squared would be s squared plus s squared plus s squared, which is 3s squared. Take a square root of both sides, we get the space diagonal is square root of 3 times the edge length. And in fact, the test loves that little factoid, so that's a good one to know also. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, let's talk about this. We have the length of two edges, and we also have the length of the space diagonal. So we don't know what that depth is, but we know that 4 squared plus 6 squared plus d squared equals 8 squared. So 4 squared 16 plus 6 squared 36, add those together, that's 52, equals d squared plus 64. D squared equals 12, so d equals square root of 12, or we can simplify that to 2 square root of 3. And again, if simplifying square roots is something new to you, please watch the video on simplifying square roots in the powers and roots section. That's where it's discussed in detail. So the depth is 2 root 3. Well, now we have the height, the width, and the depth, so we can just multiply those together. 4 times 6 is 24, times 2 is 48. We get 48 root 3, and that is the volume. Another 3D shape the test could expect you to know is the cylinder. A cylinder, when resting on one circular base, has a height of h. The radius of each circular base is r. Of course, a cylinder is a very common shape. Any can, for example, is a cylinder shape. The volume of this is pi r squared times h. And that's a really good formula to know. So basically, area of the base times the height. The total surface area of a cylinder is very interesting, and the test might ask about this also. Obviously, the top and the bottom are easy. Each is an area, so it's a circle, so it has an area pi r squared. Think about the curved side, what is called the lateral surface of a cylinder. Think about the paper label on a metal can. If you were to take a razor blade and make a vertical slice and cut the label, then you could unroll it into a flat triangle. A flat rectangle. And so here's an example. We see the top and the bottom, and imagine that's the label of the can unrolled. So of course the height of that rectangle is the height of the can, and the top edge of that rectangle is what was fitting around the loop of the circle. It was fitting neatly around the loop of the circle, so of course that length is the circumference of the circle, 2 pi r. And so the height of the rectangle is h, the width is 2 pi r. And so the lateral area is just the product of those, 2 pi r times h. And then if we add two circles, pi r squared plus pi r squared, or 2 pi r squared, that's the total area. So again, this is good to know, but do not memorize this. Make sure you understand the argument. Might even help to cut the label off a can and visualize this yourself, so that you really understand where the surface area comes from. The only other 3D shape I will mention is the sphere. You don't need to memorize anything about this. You simply need to know what it is. If they ask you for any calculations, they'll give you the formula. Every point on the sphere is equidistant from the center, and the sphere is the only shape that is circular when viewed from every single direction. So no matter how you turn it around, the silhouette it has is always a circle. I'll say that the surface of the Earth is roughly a sphere. In fact, the Earth technically is a little wider at the equator, so it's not a perfect sphere, but it's roughly a sphere, and it's a way to think about it. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, a cylinder neatly encloses a sphere so that the curve of the cylinder touches the sphere in a circle at its widest, and the top and the bottom faces are tangent to the sphere. So in other words, wrapped around, the cylinder fits snugly around the circle, and in fact they're touching right around here, where the sphere is its widest, it's touching this. And then there's a point of tangency at the top and the bottom where the top of the can and the bottom of the can exactly touch the sphere. So if the volume of the sphere is 4 pi r cubed, what fraction of the cylinder does the sphere occupy? So first of all, the radius of the sphere and that of the cylinder must be the same. They both must have radius r. The height of the cylinder must be as tall as the sphere. So it's r from the bottom up to the midline, and then another r from the midline up to the top. So that's actually a height of 2r. The diameter of the sphere. Another way to say that is that from this point at the top to this point at the bottom is a full diameter, and a diameter, of course, is 2r. So that's the height. The height is 2r. So volume of a cylinder is V equals pi r squared h, and for that h we're going to plug in 2r. So what we get is 2 pi r cubed. So that's the volume of the cylinder. So now we know the volume of the cylinder, we know the volume of the sphere, and we want to find the ratio. If we divide 4 pi r squared by 2 pi r squared, we divide 4 pi r cubed by 2 pi r cubed, then the pi r cubes will cancel, and we'll just be left with 4/3 over 2, or in other words, 4/3 times 1/2, and that simplifies to 2/3. So that's the answer. The sphere takes up 2/3 of the cylinder. And in fact, a cool historical fact, that diagram of a sphere inside a cylinder was the diagram that appeared on the tombstone of the great mathematician Archimedes. In summary, facts about the cube, its volume, its surface area, a rectangular solid, its volume and the surface area, and then the cylinder, its volume and surface area. For all of these, do not merely blindly memorize isolated factoids, but make sure you understand why these formulas are true.
Scale factor and scaling. Suppose we have a big and small copy of the same shape. So for example, here on the left, we have a small copy of a shape, and then on the right, we have an enlarged copy of that exact same shape. So it's the same shape, just different sizes. And in geometry, that's called similar. These are similar shapes. You may remember from geometry class having to prove things about triangles that are similar or compute things about them. One idea that can be particularly helpful on some of the more challenging problems is the idea of a scale factor. You don't need to know that term, but you should understand a few things about that idea. Suppose we have two similar shapes with their side lengths labeled. So these are identical shapes, and one is just bigger than the other. Notice that every side in the larger version is a fixed ratio more than the corresponding side in the smaller version. In particular, every side has been multiplied by 3. So 15 to 45, 5 to 15, 3 to 9, and 13 to 39. Every length in this one has been multiplied by 3 to produce the lengths in this one. And that's precisely what a scale factor is. The factor by which each length is multiplied is the scale factor k. And here, k equals 3. So, if in a pair of similar shapes one length is multiplied by the scale factor, so are all the other lengths. So that might be a useful way to find a missing length if two shapes are similar. Just looking at ratios of lengths is not especially interesting by itself. What is considerably more interesting, and of interest on the harder problems on the test, are ratios of areas and volumes in similar figures. So let's talk about ratios of areas. Suppose we have a pair of similar figures related by a scale factor. Here, clearly the scale factor is 2. Every length increases by a factor of 2. Suppose we know that the smaller figure has an area of 13. How would we use this to find the area of the larger figure? Let's think about squares. Let's look at squares of different sizes. So we have a square that's 1 by 1 has an area of 1. The 2 by 2 square, we increase the length by 2, we increase the area by 4. We increase the length by 3, we increase the area by 9. increase the length by 4, increase the area by 16. Increase the length by 5, increase the area by 25. I think you see the pattern here, so that if the length increases by k, the area increases by k squared. So area increases by a factor of the scale factor squared. For every formula involving area, one way or another, it involves a product of the length times the length. If you think about all the area formulas, 1/2 base times height, or s squared, or pi r squared, all of them involve a length being multiplied by a length. And if each length is multiplied by k, then length times length will give us an extra factor of k squared. The area will be multiplied by k squared. This is a general pattern that applies to any ratio of areas regardless of the shape. So let's go back to these figures. These are regular pentagons. We know that the scale factor is 2, so the area is multiplied by k squared, which is 4. If we are told that the smaller shape had an area 13, we could compute that the larger shape would have an area 4 times 13, which is 52. Here's a practice problem. Pause the video and then we'll talk about this. Okay, looks like a hard problem, but this is relatively simple to solve using the idea of scale factor. We know the ratio of AB to BC is 3/2. So AB is 3 parts and BC is 2 parts. Well, that means that AC is 5 parts. So the ratio of AB to AC is 3/5. That's a scale factor. That's the scale factor from the larger circle to the smaller circle. Well, once we have a scale factor, we want a ratio of areas, we square that. The ratio of the areas would be k squared, or 9/25, where 9 would be the smaller circle, the circle that is missing, and 25 would be the total area of that larger circle. So what's going on here is we've removed the smaller circle from the larger circle, so we've removed 9/25 of the larger circle. And if 9/25 of the larger circle is missing, how much is left? Well, 1 minus 9/25 is 16/25. Go back to the answers, and we choose 16/25. And that is the ratio of the shaded figure to the larger circle. Now we'll talk about ratio of volumes. For this, suppose we have a large supply of cubes with edge length of 1 unit. Suppose we needed a cube with edge length of 2 units. We'd need 8 of the smaller volume cubes. We'd make a square, 2 by 2 square of 4, and then put another square on top of it, and that would give us a 2 by 2 cube. And so it has 8 times the volume. So k equals 2, and we have 8 times the volume. Now think about a cube that has an edge length of 3 units. Well, what we'd do is we'd make a 3 by 3 square on the ground, then put another one on top of it, then put another one on top of it. And so we would have used 27 of the smaller cubes to make a 3 by 3 by 3 cube. K equals 3, and we have 27 times the volume. So you can kind of see where this is going. The pattern here is that as the edge length increases by the scale factor k, the volume increases by k cubed. Once again, this is true not only for cubes, but any 3D shapes whatsoever. As long as the smaller shape and the larger shape are truly similar, and the ratio of the lengths equals k, then the ratio of the volume equals k cubed. Here's a practice problem. Pause the video and then we'll talk about this. Okay. Pyramid number 1 goes from the vertex down to B. Pyramid 2 goes from the vertex down to C. Every length in Pyramid 2 is 5 times as long as the corresponding length in Pyramid 1. So they're giving us a scale factor there. The scale factor is 5. If Pyramid 1 has a volume of 8, which of the following is the volume of Pyramid 2? So the scale factor is 5. This means that the ratio of the volumes, k cubed, is 5 cubed, and that's 125. the little volume of V equals 8 is multiplied by that scale factor cubed to get the big volume. So 8 times 125, we'll use the doubling and halving trick. Half of 8 is 4, double of 125 is 250. 250 times 4 is 1,000. So go to the answer choices and choose 1,000. Between two similar figures, every length is multiplied by a constant ratio known as a scale factor. The ratio of areas is always the scale factor squared. The ratio of the volumes is always the scale factor cubed. Units of measurement. Most numbers in geometry problems are without units, but for a few real-world problems, the test does include units. So this is relatively rare, but it does happen sometimes in geometry problems. I already discussed the issue of units and unit conversions in the lesson Introduction to Motion Questions in the word problem module. So if you haven't seen that lesson, I would strongly advise watching that lesson first, because it will make everything in this lesson make much more sense. Okay. There are several common units of length: inches, feet, yards, centimeters, meters, kilometers, and miles. Ordinary lengths are measured in terms of a unit of length. Area is measured in terms of a unit of length squared. For example, square inches or centimeters squared. Volume is measured in terms of a length of unit cubed. So cubic inches or cubic centimeters, something along those lines. If the entire problem contains just one unit, then it poses no challenge. The problem is trickier and more test-like if it introduces more than one unit. For example, if it gives information in terms of one unit and asks for an answer in terms of another unit. To change from one unit to another, we need to use unit conversions. Some unit conversions might be familiar. So for Americans, certainly they would know that 1 foot equals 12 inches. Folks from other countries might be more familiar with 1 meter equals 100 centimeters. Because different units of length are used in different parts of the world, the test almost always gives these. So it's very common that this would actually appear on the test. Once you're given one of those equations, you can change it into a fraction. When we write them as a fraction, it's a fraction equal to 1, and that means we could multiply or divide anything by that fraction, and it wouldn't change its fundamental value. To change from one unit to another, we simply multiply by the unit conversion fraction that has the given unit in the denominator and the desired unit in the numerator. For example, if we want to change feet to inches, we need a unit conversion that has feet on the bottom and inches on the top. So 12 inches over 1 foot. Then we multiply, the feet cancel, and we get 6 times 12, 72. 72 inches. Changing units gets trickier when areas and volumes are involved. Suppose we have to change an area of 5 square meters to centimeters. To cancel the factors of meters, we have to multiply by the unit conversion 100 centimeters over 1 meter. We have to multiply that by that twice. That is to say, we need to multiply by the unit conversion squared. So we'd multiply 5 square meters by 100 centimeters over 1 meter, that conversion factor squared. And of course, 100 squared is 10,000, and 5 times 10,000 is 50,000. So 5 square meters is 50,000 square centimeters. Think about a square 1 foot by 1 foot. Since there are 12 inches in a foot, this square would be 12 inches by 12 inches. And we could visualize it like this. So obviously, there's much more than 12 square inches in that square foot. 12 square inches would just be one tiny column or one tiny row. The whole square foot is 12 times 12, or 144 square inches. 1 square foot equals 144 square inches. Here's a practice problem. Pause the video and then we'll talk about this. Okay, a bathroom floor is rectangular, 2 meters by 3 meters. It is to be tiled with square tiles 4 centimeters on a side. How many tiles will it take to fill the floor? So this is very typical of a test problem. We're given 2 different kinds of units and we have to figure out how to make them work with each other. So first of all, the area of that floor, that's 2 times 3 or 6 square meters. Now let's change that to square centimeters. So we multiply that by 100 centimeters over 1 meter, that's squared. 100 squared is 10,000, 6 times 10,000 is 60,000. So 60,000 square centimeters, that's the area of the whole floor. And the area of the tile, it's 4 by 4. So we want to divide that by 4 centimeters squared. And what I'm going to suggest is to make things easier, let's divide by 4 once and then divide by 4 again. So 60 divided by 4, that's easy. That's 15. Now we have 15,000. We want to divide that by 4. Well, here's one way to think about it. 15,000 is 16,000 minus 1. Well, 16,000 divided by 4, that's clearly just 4,000. And 1,000 divided by 4, that's 250. So 4,000 minus 250, that's 3,750. So that's a very easy way to get to the answer without even touching a calculator. Similarly, if we have to convert a volume, we need to multiply by the cube of the scale factor. When this rare problem occurs in the test, it almost always involves metric units because powers of 10 are very easy to cube. So 1 cubic meter, if we want to change that to centimeters, we'd have to multiply by 100 centimeters over 1 meter, that factor cubed. And of course 100 cubed is 1 million. So 1 cubic meter equals 1 million cubic centimeters. Here's another practice problem. Pause the video and then we'll talk about this. So they give us the dimensions of the pool in meters, and then we want to fill it with sand, which is given in cubic millimeters. So first of all, we can figure out the volume of the pool. The volume of the pool, 2 times 5 times 8, well that's 10 times 8, which is 80. 80 cubic meters. And then the question is, how many cubic millimeters are there in 80 meters? Well, we're going to take that 80 meters and multiply it by the conversion factor, 1,000 millimeters over 1 meter, and that conversion factor is going to be cubed. And so here it makes sense to do things in scientific notation. We get 10 to the third cubed is 10 to the ninth, so we have 80 times 10 to the ninth. Incidentally, that would be 80 billion. Using the American definition of billion, that would be 80 billion. And we could rewrite that as 8 times 10 to the 10th. In summary, change units with unit conversions, which are almost always given in the text of the problem. For areas, we have to square the unit conversion fraction. For volumes, we have to cube the unit conversion fraction. We had a video on geometry strategies toward the beginning of this module, and this video sums up all the strategies in geometry. So I'll remind you a little bit about what I said in that first video. Remember that geometry is primarily visual, and it demands visual as well as logical skills. In that earlier lesson on strategy, I recommended that you always draw a diagram, and even if one is given on the computer screen, redraw it, so that you can mark it up with what you know and what you can deduce. It may help to extend a line or to introduce variables for lengths or angles. Remember the discussion in that earlier video of look big versus look small. In other words, details of a relevant geometric relationship may be right next to each other in a diagram, or they may be on opposite sides of a complicated diagram. Doesn't matter whether the triangle is tiny or big, the 3 angles in it still add up to 180. So you need to be able to train your eye to see both the small shapes as well as the large shapes that cross over many others. Wherever there are more than two triangles, especially if parallel lines of some kind are involved, then look for similar triangles. Remember how widely applicable the Pythagorean theorem is. Anytime there's a right angle, it's worth asking yourself if the Pythagorean theorem applies. In particular, many problems about finding the length of an altitude or the length of a diagonal are Pythagorean problems in disguise. For example, suppose in the following parallelogram we are given the lengths b, y, and x. Well, certainly from y and x we could find h. That would allow us to find the area. And then, of course, once we had h, we could calculate b minus x. If we knew b and x, we could calculate b minus x, and then we could use that to find the length of d. So we could find the area, we could find the altitude, and we could find the length of the diagonal. In fact, we could even find the length of the other diagonal just by drawing a similar triangle on length CD. The triangle AB, the little right triangle with AB as a hypotenuse, we could stick one of those on the other end and then use the Pythagorean theorem again. Of course, know the Pythagorean triplets and recognize their multiples. Remember that the two special right triangles, the 30-60-90 and the 45-45-90, can be specified with very little information, but give a great deal of information. That's exactly why the test likes them. They can just throw out one little hint, then you know you have the triangle, and then you get a ton of information. Remember that every line that crosses a pair of parallel lines creates equal angles in different places. Remember all the rules about angles in circles. There are several rules there that are important to remember. In particular, remember the two times that right angles can be specified because of circular properties. An angle inscribed in a semicircle and a tangent meeting a radius at the point of tangency. Now, in both of these diagrams, I drew the little perpendicular square. The test would not have to do that. In other words, the test could just expect you to recognize that it has to be a right angle purely because of the circular properties. My final piece of advice may seem odd. Look around at your world. Look at things. Look at architectural features and designs on product packaging. Look for parallel and perpendicular lines, right angles, circles, and other geometric figures. Practice seeing some new geometric figures each day in the world around you. This will train your brain to look for geometric patterns. And these are precisely the visual skills that you need to be successful with geometry.